So I've been asked a lot about brackets or grade bins for the final grade of the course, and I just want to reiterate. So perhaps I should. I believe it was in the syllabus, but for somehow due to some reason it was not there. So the way I typically start, sort of my default brackets are to get an A. You need to have a 90+%. Then it's very easy. So to get B, it's between 80 and 90, and so on, right? So every decimal, like every 10% would give you next grade. So 70, 80, and so on. So you got the idea, right? Other grades fall in the same category. I'm not sure I understand what category means in this context. Oh, plus, yeah. There will be plus and minuses within, yeah. So like, and then so think of each of them split equally into 3 categories with the plus, nothing, and minus, yeah. Well, I think, yeah. So given the situation, I think there'll be maybe like 10 or more people like this. So to get A+, we need to have 100+%. At the moment, there are maybe 15 people with more than 100%. Yeah, so it's a good sign. So it will be a lot of fun to grade. Question: do they all have the same weight? Who they? So the way we calculate the percentage of grade, I mean this percentage, there's a formula, right? And this is announced in syllabus, like the final skill. Let me open it up. Open the syllabus. Okay. So yeah, so according to the syllabus, the 20% of the way grade is calculated. The quizzes are at 20%. So I remind you that 2 worst quizzes are removed. Oh, please. Hey guys, do you know how much more time you need? I have a conference call. Oh, thank you. Yeah, that'd be great. So like, well, I mean, I actually it's like a lecture for 2 hours, but what's your plan for the day? How much time do you need for? So are you just gonna do the nail thing, or it will be something louder? Okay, let's see how it goes. Okay. Yeah, that'd be good. Maybe like for 20, 30 minutes. Thank you very much. Okay. So the guy agreed to stop for a while. Okay. Where was I? So quizzes 20% minus 2 worse. So that's why I kind of, I mean, you shouldn't worry too much about quizzes, right? Because they're actually training. Like, so if you fail 1 quiz, that's literally nothing, like no harm whatsoever for your grade. And then the midterm was 30%. So that's a little bit more serious, but again, sort of, it's not end of the world if you did not so great. And then final will be the rest of 50. Yeah, so that's how the grade is calculated. Or will be calculated. Yeah, so now about this addition. So these are default bins, right? And then so typically I tend to loosen them a little bit. So say you got 88.7% and you're a very good person and did a lot of hard work. So then I will just bump you to the A category. So you'll get A-, instead of B plus. Yeah. So that's the idea. Correct. So I think right now all grades are in except quiz 5, which is being graded as we speak. That is correct. Yes. But those grades are not weighted. Yeah. So I think that is true. So those are just raw grades. But you can do the calculation yourself if you want. To take your best quizzes, multiply it by in percentage multiplied by 0.2, take your midterm, multiply it by 0.3, and then you can anticipate what the final will be. I think so. I think like there are 15 people out of what 70 with more than 100%. Yeah, that's about right. I think someone has 115%. So yeah, we're really doing pretty good here. Other questions? So I should send out the logistics of the final logistics maybe today or tomorrow. This is the final closed book. Yeah, so I think I need to make it. I actually leaning towards making it, allow you to use anything, but then you would be able to use Mathematica, right? So, so since we're using honor code, I think I can work through. I haven't decided yet. So one option I'm considering is that to make it open book, but no Mathematica. So like you're not allowed to use computer to check your answers. On the other hand, I'm thinking maybe it's really not a big deal because if I see that the solution is wrong and the answer is correct, then clearly the person didn't do it right. So let me get back to you on this tomorrow or later today. Maybe it will be open book, open everything. Yeah, so that hopefully will put off some stress from some people. Well, I hope not significantly more difficult, maybe a little bit more difficult. And maybe I'll give again some bonus problem so that people who have more than 100% can continue on this path. Supposedly, people who have more than 110% will get a double plus. I'm kidding. I don't think it's even possible. Registrar won't accept it. Great. Those who are just joining in, I apologize for the noise. I asked the contractors there to calm down, but not much I can do starting from here. Yeah. Actually, they opened Evans Hall for us, for professors. So you can, if you want to go, we can go. But somehow today I couldn't make it. I didn't know that there will be a problem. Will there be an emphasis on material we learned in the second half? No, I actually think to make it evenly distributed. So we had 6 sections, right? During the course, so it's 10, 12, 13, 14, 15, and 16. And think of it like having 2 problems on each section. That's what finals should look like. So I think, yeah, 13 problems. The last one is bonus, and then two problems for each section. Yeah. Okay. And I think as far as the rest of the week goes, we can, so we're almost done with the materials. I think once the lecture stops, we can switch to this review office hours mode, so we don't have to meet on regular basis. Yeah, so, right. Okay. Well, it's a summer session, we don't have RRR week, but we can have RRR couple of days or whatever. Okay, so our next story is parametric surfaces. Right. So we already discussed how to. So the idea with parametric surfaces is the same as with parametric curves. So using parameters, we can describe more complicated, more sort of interesting surfaces than with a single function, right? So typically we had a single function z of fx, comma y, and that gave us the profile, there's the shape of the curve, but that assumed that of course the function is single valued, right? So there's something that for every value of xy you have a single value of z. The idea behind parametric surfaces is to generalize that. So we have a radius vector r, which now depends on two parameters, right? Which it has a so that every component of this vector now it will depend on two parameters. So x, y, and z are now functions of variables u and v, where variables u and v belong to certain subset of the two-dimensional plane. Yeah, so this is parametric surface. We can give it a name. We can call it S. Right? We can call it S. And yeah, and it's so it's either given by a single vector equation, parametric vector equation, or three scalar equations. X equals x of uv, y equals y of uv, and z equals z of uv. So we can look at some pretty pictures in Mathematica. Every time we load Mathematica, we get another pretty picture of piano curve. Summary here, for example, this is a well, it's a parametric curve. Describes this. It's sort of two tori, right? So one torus in red, and it locks with a green torus in green. Well, yeah. So there are two tori which oriented differently, they're not up like this. They form what topologists call a link, right? But we can consider each of them individually. So there's a torus. The red torus is given by this first curve. So the so it's over here, right? So it's the first line. It depends on u and v, right? And so x component is this, y component is that, and z component is this, right? So we have a torus. So remember before we talked about so when we talked about intersect curves, which obtained by intersection of planes and other surfaces. So this dark red cylinder here is this, right? So it's a circle, right? Cosine. So x is cosine u, v is cosine, y is cosine sine u, and then the sort of parameter u here describes the position on the circle, and parameter v describes the altitude, right? So z is equal to v. right? And then if you want to do a parametric equation for the plane, right, you can write it as uv1 minus u, and that of course gives the plane, which is so this is z, right? So it's so here z is equal to, what is it? So this is z, and this is x. So z is equal to 1 minus x, and it does not depend on y, right? It's constant in y direction. Yeah. Okay, let's plot maybe something else. Oh, there's this cute picture, which is it's one of the on playground for kids. There is this slide which is covered, right? So let me try to do it here. Picture from the book. Let's try to do that. 2 plus sine v cosine u, and here they go again. 2 plus sine v sine u, and then u plus cosine v. Yeah, so see here, it looks like a it's kind of spiral here. But now it's like, yeah, so the cross section of the circle here, so let's say if you say pick say x is constant, right? So for example, well, I mean it's getting harder to kind of to get it. So, but yeah, so the cross section of this is a circle, right? You can see here. So if x is equal to, like, right, so the x position in x direction. So we have 2 plus sine v. It's like the radius of the circle. No, I think we can do it this way. So let's say we want to dissect it vertically, right? So from here, and then every time you make a section, you'll have sort of an ellipse, right? And then it will be ellipse, like a circle with radius 2 plus sine v. And as v changes, kind of this radius will change. However, if you look vertically, right, in z plane, right, so then so this just shift by u. Let's maybe do minus 5 to 5. Right, so yeah, it goes like this. And then it's actually a circle. It's a circle cross section in that pipe. So you go on the playground with just a little kid, a little brother or sister or nephew, and then you throw them into this thing, and they scream and fall out. From here, very happy with the electrized hair. So the hair becomes like, looks like a hedgehog or something. After they write it 2 or 3 times. Yeah. So let's try something else. Let's maybe do it in green. How about if you take, say, 3 sine, let's call it those variables different, sine phi, cosine theta, and then y is equal to 3 sine phi sine theta, and z is equal to 3 times cosine theta. So 5 varies between minus pi and pi and theta. So question, what is this going to be? Yeah, okay, really bad, we will need this. what do you think this curve will describe? This surface, excuse me, surface. Look at this formula and think, yeah, sphere of radius 3. Well, not, I've done something wrong. Okay, what did I do wrong? Sin phi cosine theta. Oh, wait, so sin phi sine theta. Oh, cosine phi, yeah, that's right. There we go. Thank you. Yeah. What was before was something self-intersecting. Yeah. Yeah. So that's the sphere of radius 3. See, it's very nice. You don't have to do any square roots. Beautiful function, sort of product of trigonometric functions. Stuff like that. So there's you can have a lot of fun with this kind of things. Yeah. So you can see it gives you immediately a lot of freedom and a lot of creativity of how to draw surfaces. You can pretty much draw anything. Yeah. Now, so a couple of comments. So when we have this, so locally, it still looks like a part of, like a patch of a, you know, of a regular surface, right? So you can always choose coordinates, say, you know, you want to describe only what happens here in kind of this part of the torus. So you take the equation, right, and then you can, in this around here, you can actually solve this. You know, it might be possible, it might not be possible, but like 1 second. So the locally it does look like z equals f of xy, or if you cannot do that, it will look something if you look from here. So now, if you try to describe this patch of the torus of the surface, it rather may look like x equals some function g of z and y, right? So it's up to you what to pick as the z variable, right? The idea behind parametric curves and surfaces is that, well, you can incorporate all that into a single formula, right, which is much more powerful. Surfaces are also called in geometry two-dimensional manifolds. And so this word which you probably have heard, manifold, right? And basically what is a manifold? So in a nutshell, it's a geometrical object which is glued together from those patches, each of which looks like a copy of two-dimensional, an open two-dimensional, an open set in two-dimensional space, right? So say you take these two patches and then you can sort of glue them with these two patches, and then there's something inside. So each of them looks like a slightly deformed set, right? So some open set D. Openness is important for topological reasons, but so although those patches allow it to overlap, right? And then at places where they overlap over here, right, you have a sort of both descriptions should give equivalent results. So for example, if in this black patch, you have this function z equals f of xy, and in the green patch, you have z is equal to, say, f tilde of xy, right? So then there should be a, yeah, so then there should be, you should be able to find a connection between f tilde and f, and like there must exist explicit formula. So this formula, which allows you to switch from one description to another, is a part of data of the manifold, right? So essentially, the manifold is basically it's a rule, right? It's completely defined by a rule of how to glue those patches together. Sometimes they're called coordinate charts or coordinate patches for this matter. So for example, how can we think of a torus this way? So you probably know that to get a torus, you take a square or rectangle, and then you would identify its opposite sides like this, right? So if you do it once, you make a tube, right? And then if you do it, and then you would sort of close it up like this. You would, and then so clearly that's not, that itself does not look like a, like a patch, but what you can do, you can cut it in half like this, right? So so these points get identified. All these 4 points become a single point on the torus, right? These two guys, this 1 and 2, will become 2 disks, right? So on this diagonal would look like a a certain path on a torus, which would come out over here and then come back here again. So it will wrap around vertically and horizontally once, and it will cut the torus into 2 disks. Yeah, that's one of the ways to make a torus. Now, say if you want to make a sphere, how can you make a sphere out of those things, right? So we all know this. We take a northern hemisphere, and we can take a little bit more, like sort of go a little bit below the equator, around the North Pole, and then another patch would be, you can take the southern hemisphere, take a southern pole with a southern hemisphere, and a disk like this would go around, right? And then in the equatorial region, these 2 guys will overlap over here, and your description should be like the coordinate description in that north hemisphere should agree with the coordinate description in the southern hemisphere. So in this red common region, the both descriptions should give you the same space. So there should be an explicit formula of how to do it. So one of them is the so-called stereographic projection, right? So if you take, let me draw it here. Cut everything. So there are 2 ways. So you can put it's used in complex analysis. I think I mentioned it before. To put a sphere on the plane, and then you would draw straight lines from North Pole through the sphere, right, towards the plane. So this line will intersect sphere at some point, and it will intersect the plane, right? So this way you make a bijection between every point on the plane and every point on the sphere except the North Pole, right? So therefore this 2 sphere minus this North Pole, so this P is in bijection with the 2-dimensional plane, right? So it's not the whole sphere, right? So you get rid of 1 point, and that's a big deal. Technically, topologically, it's a different space, right? So how would you recover that space, that point? Well, you need to take a different coordinate description. You take a plane on top of it, right? So this, which is tangent to the sphere at the North Pole, and you'll do the same identification from the South Pole. Right? You would do it like this, and then again, it will intersect a point on the sphere here, and then point on the plane there. Now, this point here you can identify with the corresponding plane down there, and then you should be able to write a formula that relates to you. Sorry, I'm going to rephrase that. So now the same point on the sphere has 2 different descriptions. Every point on the sphere has 2 different descriptions, except poles, right? So this green dot that I just circled has 2 descriptions. So if you draw lines through it, right, it will give us 2 images. One is the green dot on the bottom, and another one is this blue dot over here. So let's call this W, let's call this Z, right? And by doing some simple analysis with the triangles, you can show that as complex variables, W is equal to 1 over Z. Right, so and you can rewrite, if you write a real imaginary components, you will tell exactly how xy coordinates of the bottom on the bottom is related to the xy coordinates on the top. Yeah. Right, so that's the sort of this manifold description of what the sphere is. That was a little bit off topic, but I thought it's a good place to put this in. Questions? Okay. Right. Okay, so then we can talk about a particular example of those surfaces is the surfaces of revolution. And so, sort of the name speaks for itself. You can, so for example, sphere, right, is a surface of revolution. So you can, it can be obtained by revolving a half circle, right? So basically, you can draw a line through any of this, any line that goes through the center of the sphere, right? And then we can take a circle. So it passes through one of green. The points here and somewhere there, right? And then you would just spin it around. You know, the semicircle which you get here. So you'll get a sphere, and there are infinitely many ways to do so. But in general, what you would have is that you would do the parametric plot, right? And then you would say that, so let's just switch the description in terms of just x and y. All x are certainly x and theta. Let's say x varies between some values, and then theta between 0 and 2 pi, and then the x component is just equal to x, right? So we would simply go along the axis of rotation, right? And then say we take, say y component is equal to, for example, sine x cosine theta, and z component is equal to sine x sine theta. So yeah, so you see that this is this is the surface of the cone. Can be minus bigger. Yeah, well, yes, it's kind of an interesting phenomenon here, right? So you have a so x goes in this direction, right? So x itself is a parametric, it is a parameter, right? Sort of which uniformly changes along the axis. Green is kind of boring. Okay. Yeah, that's more fun. So, right, so x variable goes this way, theta variable goes that way, right? And then the, yes, basically on y and z, in y and z you have a circle, right? In the, yeah, so you have a circle of radius 3 sine x, right? Which changes in, which has the yeah, so it's a circle, like so in y and z plane, it looks like a polar coordinate description. So these two guys, right, they give you a polar coordinates, but you can dissect this by a plane, by the YZ plane, and then these guys will show you the sort of the polar coordinates description of that plane. So you have for every value of x, you draw a circle of radius 3 sine x in YZ plane. right? And that's why it looks like that. So in general, surfaces of revolution would look like this. So you have right, you have so x equals to x. Of course, you can pick instead of x, you can pick y, basically any direction that you like. Then you say y is equal to, so, and then there's this f of x is a profile function, which in this case is a sine, but it can be anything that you like. And then in YZ plane, you make a circle. Right, so here theta always varies between 2 pi and 0, and then x varies whatever you want, right? So it belongs to some domain of definition of function f. So that's how you would do a surface of revolution. Let's draw something else. Let's draw. Why the carrier was 3 all around all the time? Yeah, maybe I should allow Mathematica for the final. Yeah. What does it look like when you go to the doctor's office? You have those things in the when they stick it in your ear. Yeah. Wormhole. Yeah, that's right. Although it's typically not exponential, right? So, I mean, it's exponential in some coordinates. Yeah. So in general relativity, when you talk about this black holes and singularities, like you can have different coordinates, but the certain quantities that you calculate, they don't depend on the choice of coordinates. So yeah, so wormhole will look exponential in some coordinates. Or it's like a 2-dimensional slice of this wormhole because it goes to infinity here. Okay. It's called autoscope. Yeah, that's the name for the thing, right? Okay. So our next story is tangent planes. I think I can just draw it here. A very long, yes, exponentially long. So if our function r of uv, right, is a vector function that behaves like x of uv it has components x of uv, y of uv, and z of uv, right? Then need to determine the direction. So remember what a tangent plane is. Okay, maybe you can just draw some of them here. So you can see. Let's start off with an example, and then we draw on the example. So here, and then we draw the plane which has coordinates say I want to have x equals 0, and then just oh no, that will cut through. I think I want the other one, so I want to have 1. Yes, 3 rather. Okay, and let's sort of go from like this, yeah. And so that's like this, right? So it's a plane that is tangent to the sphere, right? Well, so how this plane should behave? So the bigger. So the we can cut it through the with a so the so let's so remember I told you about two different descriptions, several different descriptions when a little patch, right? So if you look at the patch over here of the sphere, then we can actually write it as a function of two variables, right? As a surface. So in this case, we can say that it's z is equal to square root of r squared minus x squared minus y squared. Second. Yes, minus y squared, and then sort of here x and y will be the parameters which we'll use to describe this here. Now, in general, we don't have x and y. We have parameters u and v here, right, which belong to certain subset. Which belong to certain subset d to d as a subset of R2, right? And if this is the formula for which describes the parametric surface, right? So then we should have in order to describe the tangent plane, right? We need two vectors, which are which will give us the tangent plane, and each of those vectors should be tangent, right, to the should be tangent to a curve, right, which belongs to on the surface, right? So we have a curve in this example. We have a circle that goes this way, and then we have a circle that goes that way, right? And in a certain local coordinate description, we have it is described by parameters u and v. So think of it as if you can, switch to the explicit parameterization and say that z is equal to square root of r squared minus x squared minus y squared, right? And in this case, we know what to do, right? We already have the formula for the tangent plane in this case, right? And now just replace x, y with u and v, right? And then you'll get you will get the following. So we need to have we need to know explicitly two vectors, right? One of them will be partial derivative of r relative to u, and the other will be partial derivative of r of radius vector r with respect to v, right? And then we know what to do. We just take the cross product. Right, so the normal vector to the tangent plane will be the cross product of ru with rv. And so that will be the that will be the equation for the normal vector, and then we just do the sort of define write the equation for the tangent plane as usual. So if this point is well r naught r0, right, and then there's another point on the plane, so with coordinates x, y, and z, right? So then we just draw this vector here and declare that the dot product between the normal vector and the vector on the that connects the point and some other point on the plane is equal to 0. Okay. So I think for this one I'm going to switch to the node taking place. So this is the idea. Let's it will stay in the in the recording, I'll also send you the Mathematica video. How can I do the, maybe I can just do the print screen. I always forget how to do it. How to do print screen on Mac. Let's see who will find it faster, me or it's Command Shift 3. Yeah. So we're doing. So that's in. So we calculate RU, which has components XU, YU, ZU, and RV, which has components XV, YV, ZV. Right, so then the normal vector will have coordinates RU cross RV. Right. Yeah, and they say the equation, as always, right, the equation for the tangent plane will be n dot r minus r0 is equal to 0, where r0, so it's tangent plane, there's only one, right? So tangent plane at r0, which has coordinates x0, y0, z0. Yes, and R has here R has components x, y, z. Right? It's an arbitrary point on the plane. Okay. So that's the equation, which we already know for a very long time. It's just now we have a specific recipe of how to calculate the coordinates of the normal vector. Right, so maybe let's do an example. So let's calculate. Say have the following surface, which is given by coordinates u squared, v squared, u plus 2v, and then calculate at point, derive the equation for the tangent plane at point r0 with coordinates 1, 1, 3. As you can see here, this is achieved when u is equal to 1 and v is equal to 1. So indeed, such a point belongs to the plane. Let's calculate derivatives. So it's equal to 2u 0, 1. RV is 0, 2v, and 2. Now the cross product and it will be equal to minus 2v minus 2u, 4u, excuse me, and then 4uv. Right, so, and And then then we need to evaluate this at point R naught, which corresponds to having u equals 1 and v equals 1. It's -2, -4, 4. Right, and then therefore the equation for the tangent plane will read as so it's -2 times x minus 1 minus 4 times y minus 1 plus 4 times z minus 3 is equal to 0, or minus 2x minus 4y plus 4z, and then it's what? It's plus 2 plus 4 minus 12 minus 12 minus 6 is equal to 0. We can cancel it in minus, divided by -2, so it's x plus y minus 2z. One second. Yeah, minus 2z plus 3 equals 0. Yeah, this is the answer. Scroll for a second. I didn't. Definition of S. Oh, just, yeah. I mean, it's kind of written a bit misaligned, right? But what I meant to write is that it's well, it's a rule that assigns that R of UV is equal to X of UV, Y of UV, Z of UV, such that you can put either a column here or like the vertical line as we do. Oh no. Somehow Zoom is unstable today. I'm not sure what's the reason. I'll share that again. Yeah, you just take partial derivatives of the components. That's right. Yeah. How do you get equals stuff equals 1, right? So no, so R of UV is a vector function, right? It's a vector function of well, 3 components, and each of the components is a function itself of u and v, right? So remember when we talked about chain rule, right? For functions of many variables, the rule was that we take a derivative of each of the parts and then multiply it by partial derivatives with respect to each of the variables. Okay, I think I have to restart Zoom on my iPad. Jay, is that does that resolve your confusion? Oh, okay, you're sending it, okay. Any other questions on its parametric derivatives? Yeah. Okay, good. So this brings us to the next topic, which is calculating of the surface area of an arbitrary surface, which is given by parametric equations. Right, so let's look at this function again. I'm going to write it, so R of UV is equal to X of UV, Y of UV, Z of UV, right? And we can think of this vector function as a rule that maps in the UV plane so it maps things to the to three-dimensional space, right? So it's it maps it to a surface. So in the UV plane, we can think of let's first think that our region D is a rectangle. Right? It's always when we do integrals, it's easier to do rectangles, right? And then we can take a partition of this rectangle as usual when it happens when we do integrals, and then we map it to the three-dimensional space, which it has coordinates x, y, and z. And here we have some surface. Right. So we can ask ourselves what happens with a small rectangle over here. So as it maps to the surface, its image. So say put a point. So as always, we can give we have a partition of. Let me not write down the full kind of setup for the integral. So we know what's going on, right? So we take a partition of the u-axis, we'll take a partition of v-axis, and then each of those lattice points will have some coordinates. So let's say this red point will have coordinates ui, vj, right? Its image here will be point, let's call it p, ij, right? And then let's say that the width of this rectangle is delta ui, and the height is delta vj, and its image is this some curved small rectangle, which we can call Sij. Right, and in order to find the surface of the area of the surface, it suffices to find the area of this Sij, and then we just take the sum over all I and j, and then we take the limit, right, as delta ui goes to 0 and delta vi goes to 0 for all delta ui and delta vi, and then that will bring us to the area of the surface S. So let's call it surface S. So let's write it down here. So surface is what? It's this thing where u and v belong to D, which in this example is a rectangle. It's a subset of R2. We can call this is surface S. Right? Assuming those limits exist, this double sum will converge to the area of the surface. Okay. So now our task would be to understand how to write down this in terms of the data of this vector function, and you probably already know that it has something to do with the partial derivatives of the vectors r in u direction and in v direction. So indeed, so let's maybe magnify it a little bit. That's the rectangle here. and that's its image after we apply the function. And so we can draw this point Pij, this point Ui Vj, and then this vector here, right, will be nothing but derivative r prime u, its length, it's r prime u times delta u, right? And this vector here will be r prime v times delta v. Why is that? Well, let's look at the original picture again. So you take the, say, we'll look at the curve that goes like this, right? What is the image of this line? Well, it will be some curve over here, right? And then this vector r prime u will be the tangent vector to point Pij, which go in this direction, right? So similarly, if you take another line which goes vertically, its image will be here. So it's different color, but anyhow, so and this will be vector r prime v, right? But now, since we want to understand, since you want to calculate the area, right, we need to actually know the length of this vector. Right? And as you know, I'm going to remind you what happens in a function of one variable. So if you have a function y equals f of x, right, and then you have two close points which are separated with delta y, and this is delta x, right? So in linear approximation, delta y is equal to the derivative f prime of x delta x. So that's exactly what happens here, right? So now we have two vectors in two orthogonal directions. So the length of this vector here will be r prime u delta v, and length of this vector will be r prime v delta u. Okay, so that allows us to write down the formula for the area of Sij, which is of course given by the cross product, the absolute value of the cross product. So we take r prime u, well, evaluated at that point, right? So it's r prime u cross r prime v, what at ui vj, and times delta u I delta vj. Right, so the area will be the cross product. You can think of this area as a vector. This is A of Sij that looks up, and it computes the area of this thing. And then finally, in order to, after you take the limit, you'll get the integral. Right, so therefore the area of this S, of surface S, will be equal to a double integral over d ru cross rv dA. Yeah, so that's the complete formula. So as a sanity check of the formula, let's calculate the area of the sphere. So there's a sphere of radius r. So we now know what the radius vector is. A sphere can be given by the r of theta and phi. Right, you can have it like this, it's a vector function whose components are given by r sine phi cosine theta, r sine phi sine theta, and r cosine theta. Cosine phi, again, I'm forgetting it because, like I told you, in my calculations, I swapped them around and use it differently. But anyhow, so that's the thing, right? So now here, so our domain D in this case is actually a rectangle, right? Because these are spherical coordinates, and D here is a set of when theta varies between, I mean, be careful, theta from 0 to 2 pi, that's the polar angle, and then phi varies between, I should use phi with the same font. It's, and phi varies between pi and minus pi. So it's rectangle. You can just use the formula directly. Right. So yeah, we'll also let's calculate before doing the formula. Let's calculate the normal vector first. And so, oops. Right. So this normal vector, which is RU times RV. Right, so you have I, J, K. Now we can take out the r squared, right? So we don't have to carry it around. It will be overall factor, and then well, u and v here play the role of theta and phi. So let's do it this way. Let's do first phi derivative and then a theta derivative. Right. So phi derivative will be cosine phi cosine theta, cosine phi sine theta. You need to make it a bit bigger, and negative sine phi. And now we do the theta derivative. It's negative sine phi sine theta, sine phi cosine theta, and 0. And which brings us to r squared multiplied by sine squared phi cosine theta. Then it's sine squared phi sine theta minus, oh, I'm sorry, yeah, so something's wrong. Yeah, so then, yeah, sine squared phi sine theta, no minus, and then the k component will be cosine phi sine phi cosine squared theta minus or plus cosine phi sine squared theta. Right, so overall it becomes cosine phi sine phi. Okay, and now we need to calculate the absolute value of this normal vector. Right, so it will be square root of sums of squares of these guys. Right, so it will be sine to the fourth phi cosine squared theta plus sine to the fourth phi sine squared theta cosine squared phi sine squared phi, and then r squared. And so what do we have here? Yeah, so we can combine. So here, these two guys will give us sine to the fourth phi, right? And these guys give us so we can think sine to the fourth phi as sine squared phi times sine squared phi. And then here we have one sine and one cosine, so we're gonna get 1. So after that we get r squared times square root of sine squared phi. Right, and because the way we choose phi, right, so sine is always so sine will be positive. So sine is positive if we go from 0 to, well, it should be actually absolute value, right? So it's equal to r squared times absolute value of sine phi, right? So because, well, yeah, because, well, it's absolute value of that, right? And then we have to pick the positive branch. How do you simplify the last term to cosine phi sine phi? Yeah, so here this one. Yeah, so you have you have cosine phi sine phi here, cosine phi sine phi here. You factor it, and then you have cosine squared theta plus sine squared theta, which is 1. Yeah. Okay. Why isn't the range of phi from 0 to pi? Actually, yeah, I think you're right. I think, yeah, we do. It's from 0 to pi. Yeah, never mind. Yeah, I was confused about something else. Yeah, so it is positive indeed, because phi in the sphere it varies from 0 to pi. So phi between pi. I believe it just came from another, again, the same confusion with notation that I had. Yeah. So sine is positive here, so we just take the plus sign. Yes. Thank you. Okay. Yeah, and then we can just evaluate the area, right? So it's a very simple integral. It's over d of r squared times sine phi d theta, right? So it's integral of d theta from 0 to 2 pi, and integral from 0 to pi is r squared sine phi d phi. So this integral is equal to 2, as we know. This integral is equal to 2 pi. So we get the correct answer, which is 4 pi r squared. Okay. A particular example of this formula is when we actually have an explicit graph of function z equals f of xy. we had a similar explicit formula for when we talk about length of curves, right? So once we have explicit formula, z is equal to f of xy, right? So then we can just parameterize r as x, y, and f of xy, right? So then the derivatives would go as follows. So r x is equal to 1, 0 fx, ry is equal to 0, 1 fy, and then the normal vector would look like ijk 1, 0 fx, 0, 1 fy, and that has components minus fx, minus fy, and 1. So then we need to calculate the absolute value, and then the area will be equal to double integral over d square root of 1 plus fx squared plus fy squared dx dy. And so that should remind you so when we had a length of the curve, which is given by explicit function, we also had 1 plus the derivative squared dx, but now it's a surface, so that's why it's a double integral. Okay. Okay. So let's do maybe one example. Let's say we have a paraboloid x equals to z equals to x squared plus y squared, and then that lies under the plane z equals 9. And so it would look like things like that, right? Where, because it's a square, we have x and y varies from -3 to 3. Right, but it's essentially the cross section is a circle, right? So it's well, should not try to write it like this. Well, once we set up the integral, it will be then easier to switch to to polar coordinates. Right, so the area will be equal to the double integral of d. So d here is a disk, right? So so d is disk is a set of points in 2 planes, so that x squared plus let's recall the 9. Right, so it's a disk centered at the origin with radius 3. So we integrate of this thing over, well, the 1 plus 4x squared plus 4y squared. I'm just looking at the formula above, right? Dx dy. And then we switch the polar coordinates. So it will be integral from 0 to 2 pi d theta, and then integral from 0 to 3 dr. Then remember that there's this Jacobian, which is equal to r, 1 plus 4r squared. Okay, now let's call this u. So u is equal to 1 plus 4r squared. Du is equal to 4r dr. And then when r is equal to 0, u is equal to 1, r is equal to 3, u is equal to what is it? 37, right? It's 4r squared, right? So the or 8, thank you. Yes, 8r. Right, because that 4, right? So and then yeah, so the answer is equal to integral is equal to it's 2 pi integral from 1 to 37 over 8 u to the 1/2 du, which is equal to pi over 4 2/3 u to the 3/2 from 1 to 37, which is pi over 6. Yeah, so 37 roots of 37 minus 1. Yeah. Okay. Okay, so next generalization of this story is so far we found surfaces, areas of surfaces, which you can think of integrating an identity function over that surface. But now we can now integrate any function, right, which is defined on the surface. So surface integrals. And so what they're saying, kind of, so say we have a function f of x, y, and z, right, which is defined on a surface. So it's defined everywhere, right? So it's a function, from R3 to R, but in particular, it's defined on a surface just by so say you have a surface S inside R3. So if the function is defined everywhere in R3, it's also defined on the surface as a subset. Right? It's naturally induced on the subset, right? And then we can construct this similar Riemann sum, right, as before. We have the double sum of I and J, areas of the segment as areas of this little parallelogram, curved parallelogram Sij as before. But now we can multiply it by value of this function at some point Pij, let's call it star, which means that we can evaluate it everywhere, right? So so say this is this parallelogram, and this is point Pij, and then we are free to evaluate the function anywhere inside it. Same way as when we evaluate Riemann integrals, we don't have to calculate the function like on the boundary of this of the partition, or we can put it inside. So if the integral exists, right? So then the answer should be equal to the answer should be the same everywhere. right? And then, so by definition, this thing as delta ui goes to 0 and delta vi goes to 0 becomes the integral, surface integral of function x, y, z. Well, let's call it ds now, because it's, we can put it in both, or actually dA is fine. So, yeah, otherwise it's too confusing. Yeah, so this is the integral of f over surface S. Right, and the it's easy to write the formula. So after taking the limit, we get that. So this integral, well, it becomes double integral of f of r. So if the surface S is given by vector function r of uv, such that u and v belong to some subset D. So what you need to do is, so you need to plug in, instead of x, y, and z, x of uv, y of uv, and z of uv, right? Put it inside f, and then integrate it with the standard formula that we have, like this. So the surface integral, we can call it I, is given by this formula here. Okay. So let's do an example. Is integral over d? Yeah, thank you. Integral over d. So the calculation wouldn't change much, except you just need to multiply by the integrand. Right. So now let's integrate x squared over sphere, right, where S is the sphere of radius 1. Right, so we already know the example. We already know the answer for the normal vector here. So normal vector, absolute value of the normal vector is equal in the spherical coordinates, right? So we switch to spherical coordinates where x is equal to sine phi cosine theta, y is equal to sine phi sine theta, and z is equal to cosine theta. So as we calculated for the sphere of unit radius, this absolute value of the normal vector is equal to sine phi, right? And then therefore what we need to do is just to calculate d, which in this case, right, so theta varies between two, it's a rectangle. So it's theta between 2 pi 0 and 2 pi, and pi between 0 and pi. Okay, they're getting louder, but we're almost done, I think. Yeah, so the And then here we take x squared, which is sine squared phi cosine squared theta, right? And then remember, when we do integral in spherical coordinates, we have to multiply by r squared, by r squared sine phi d phi. So r squared here is 1. So we integrate, so the Jacobian of the change of coordinates will be sine phi d phi, and then d theta. Okay. That's the integral. So here, everything factorizes. So we have theta integral cosine squared theta d theta multiplied by the phi integral sine cube phi d phi. Right. So this integral will do by using the trigonometric substitution, right? So it will be 1 plus cosine 2 theta over 2, right? And the integrated over period will only 1/2 will survive. And here we can do the we can use the, you can write sine cube theta as it's sine squared times sine, and then we do so sine squared is 1 minus cosine squared phi d cosine phi with a minus sign, right? So after integration, that will give us, so the first integral is equal to pi, and the second will be equal to, so it's minus cosine phi plus 1/3 cosine cubed phi, where phi is from 0 to pi, right? And that's equal to, so cosine, yeah, so cosine phi, when we have pi is -1, right? So it's 1 minus 1/3, and then when it's 0, it's 1. So it's minus 1 plus 1/3. So it's equal to 4/3. And that's the surface integral. Right, and similarly, you can do, if you have a formula with explicit description z of z is a function of f of x and y, then you would just integrate it as before. So if then we can have the sorry, actually let me if the surface is, so if s is given by let's f is already taken, let's take a different function. So if surface S is described by equation z is equal to g of x y, then you want to integrate function f of x y z over s, right? So then it will be equal to double integral over d, right? Where now it's spanned by x and y. So it's f of x comma y comma g of xy times square root of 1 plus gx squared plus gy squared dx dy. On the last line towards the left, did you get phi term from the integral? That is correct, yes, because the integral over cosine double angle is 0, right? And so twice diffused. So we have 1/2 in integral from 0 to 2 pi, that gives pi. Yes, it's you just don't see it's a 2 pi here. So, okay. So then, well, we're almost done. We need to talk about sort of we're going over the same kind of chain of modifications, sort of chain of sort of building the same construction as we did with the line integrals. So first we define the line integral over the vector field, over the function, and then we define line integral over the vector field. So here we now define the surface integral of a function, and now we can define the surface integral of the vector field. Right, so, well, it should not be surprising now what to do. Integrals of vector fields. So if there's a vector field, well, which is a vector, an integral is a number, right? So we need to make a number out of a vector, and the best way to do it is to take the dot product, right? And luckily, we know exactly what to do because we have a surface. We know how to calculate the normal vector to this parametric surface. Right, so we have those tangent vectors, Ru and Rv. Right, and then there's a normal vector n, which is the cross product, and say that you have a vector field F it's a vector field, right? So we know it's a function from R3 to R3. So if it's defined everywhere in space, it's also defined on the surface just by if you restrict the if you restrict it to the surface, right? So at every point on the surface, we can just calculate the dot product. So take vector F, we take the dot product with n, we get a scalar function, and now we can integrate that function over the surface. And this is by definition the integral of a vector field F over the surface S. Right, so same idea as before with curves, with line integrals, only now it's we do it we take the integral over the over the surface. And another name for this is the this integral is also called the flux of vector field F across surface S or through S. right? Now, when I say vector, normal vector, I already imply here that it's a unit normal vector. So here we have that absolute value of n is equal to 1. So if you want to write an explicit formula, then it would look like this. So the more explicitly, you have it's an integral over s f ds, right, is equal to integral over s f dot this vector, normal vector, which is ru cross rv, divided by its length. But then when we integrate over the surface, we need to multiply by this thing, right? So it's ru cross rv absolute value dA, right? So now dA is an element, so here it's the d here. It's over d. And yeah, so therefore things cancel, so we can write it as integral over d in the explicit parameterization of surface S. Again, so say S is parameterized with R of u and v. Right, so we have F dotted with RU cross RV dA, right? Or it's a triple product. So we need to calculate the triple product of F, RU, and RV. Right, and that will give you the flux. Okay, so I think well, yeah, that's eventually today is quite. I think there's quite a lot of information. So let's just do the example, and then we probably can go. So let's calculate of the flux of the Euler vector field through the sphere. So we have a sphere of some radius, right? And then there's a vector field that goes sort of from the center, like this. So F is equal to x, y, z. Right? We know what the normal vector is, so we're going to switch to polar coordinates, to spherical coordinates, excuse me. So in spherical coordinates, normal vector was equal to well, yeah. Let's. I think yeah, it's probably easy to recalculate, right? So if f is equal to yeah, so it's oh yeah, so right, so you need to do the calculator. So this will be x is well, it's a different example in the book, but here let's do this. So if x is equal to yeah, so it's sine phi cosine theta, sine phi sine theta, cosine theta, right? And the RU or R phi let me scroll. Oh, yeah, actually, so R phi cross, we already calculated that third, right? So R phi cross R theta, as we calculated before, was equal to sine squared phi cosine theta, sine squared phi sine theta, and then sine phi cosine theta, or sine phi cosine phi, excuse me. Yeah, so now we take the cross product and the dot product of these two guys, and then we integrate in over D. So our integral will be, well, from 0 to pi d theta, from 0 to pi d phi, of what? Of sine cube phi cosine squared theta. So I'm just multiplying components, first by first, second by second, and third by third, plus sine cube, there's a typo here, right? So there's a phi. So phi here, sine cube phi, sine squared theta, plus sine phi, cosine theta. So these two guys give us sine cube phi. Yeah. And these guys, well, we can just integrate them over and think so this is what it's sine q phi, right? And when you integrate sine of 2 phi over the period, you'll get 0, right? So therefore, this will not contribute. And also, if you integrate cosine theta over the period, you'll get 0. So that this will not be important. So the whole integral will be equal to 2 pi multiplied by integral from 0 to pi sine cube phi d phi. And we already know what this is, right? So it's, again, we do it as 1, well, we can get it to, so it is equal to what, 4 thirds, right? So I think this integral is equal to 4 thirds. So it's all equal to 8 pi over 3. So we have this integral above, so it's in here, right? So this was the integral, so it was equal to 4 thirds. Yep, that's the answer. Okay, yeah, so that's the flux. That's the flux of the Euler vector field through the sphere. Okay, so tomorrow we'll finish up with this, and then we'll talk about the divergence theorem. So how the flux of a vector field through a surface is related to the divergence of the vector, is with the volume integral of the divergence. Z is cosine theta, right? That's the sphere. Oh, phi, sorry. Yeah, I think you're right. I think you're right. Yeah. Okay, thank you. See, I mean, I really should either you stick with my notation, but still the answer will be 0 because yes, here we get the yeah. So the no, that's yeah. Thank you. Yes, we kind of it's only phi. There is no theta. Final will be on Friday. Yeah, I'll make an announcement. Yeah. So we only have phi's, right? Okay, so then it's not quite right. It's like not the first time we'll be given. Yeah, so plus cosine squared phi sine phi. Yeah. So we have then we have to do two integrals, right? So then we can integrate this guy. We'll have integral from 0 to pi cosine squared phi sine phi, right? And that's equal to what? It's equal to minus 1/3 u cubed, right? And u varies from -1 to 1. From -1 to 1, which is equal to 2/3, right? And then yeah, so it will be more. So yeah, otherwise it should be right. It should be basically it should be 2/3. It should be 2/3 for each direction. Thank you. Yes, it's 2/3 here. So it's 6/3. So overall it will be 12. 4 pi. Yeah, that's what it should be. Thank you. Overall integral is equal to 4 pi, which would be indeed the area of the sphere. Yeah. So it's 2/3 here. So like overall integral is equal to 2 pi multiplied by 6 pi 6/3, or multiplied by yeah 6/3, which is 4 pi. Yeah, there you go. And now that looks better. Okay. Great. So we'll finish tomorrow, and then we'll already start. You can prepare your questions for tomorrow. Once we're done with the material, we'll start and answer questions, and we'll do another review session on Thursday. Okay. Great. See you guys tomorrow. Bye.